We are accustomed to believing that the universe exists independently of our presence. When you step out of a room, you take it for granted that the chairs, the tables, and the artwork remain precisely where you left them, maintaining their shapes, textures, and colors in the dark. We assume our observations are passive, that looking at the cosmos is akin to pulling back a curtain to reveal a pre-existing stage. But when you look closely enough at the fundamental building blocks of reality, this deeply intuitive worldview dissolves entirely. The act of gathering information about the universe does not simply uncover a hidden truth. It actively forces the universe to make a choice. This is not a statement about the mundane disruptions of everyday measurement. When a doctor places a thermometer under your tongue, the cold glass absorbs a minuscule fraction of your body heat, marginally altering the very temperature it seeks to record. When a biologist tracks an animal through a forest, the rustle of leaves changes the creature's trajectory. These are engineering hurdles, trivial complications born of physical contact. The weirdness of the subatomic world is far more radical. In the quantum realm, a physical property does not merely wait around in a state of quiet concealment until a scientist comes looking for it. Before a measurement occurs, that property is fundamentally, explicitly undefined. The universe does not possess a secret answer that we are simply too clumsy to find. Rather, the universe has not yet bothered to decide what the answer is. To declare that reality is inherently undecided sounds like a retreat into philosophical mysticism, a flight of fancy reserved for late-night debates, rather than serious laboratories. Yet, this is the inescapable verdict of the most triumphant, intensely verified theoretical architecture in human history. Quantum mechanics does not merely work. It works with a terrifying degree of precision. It predicts the behavior of the natural world to a staggering number of decimal places, easily outperforming classical physics and outshining even the cosmic elegance of general relativity. Since its formalization in 1925, no rival model has managed to displace it, and no experiment has ever caught it in a lie. If we choose to trust the mathematics that has given us the modern transistor, the laser, and the microchip, we must also trust its deeply unsettling implication. The physical properties of the universe do not truly exist until an interaction demands them. Our minds naturally rebel against this concept because our daily lives are anchored in a macrocosm of predictable permanence. A copper coin resting at the bottom of a pocket has a definite face pointing upward, whether or not you reach in to check it. A mug of coffee has a specific volume and temperature, regardless of who holds it. The moon does not vanish or dissolve into a hazy cloud of possibilities the moment humanity turns its collective back. Because our evolutionary history prepared us to dodge predators and gather food in a world of macroscopic certainty, we naturally project that certainty downward onto the subatomic landscape. We assume an electron must possess a clear trajectory, a distinct spin, and a precise home. But the experimental data gathered over the last century shows a callous disregard for human intuition. Time after time, the universe has responded to our deepest probes by confirming that it is not a clockwork machine of predetermined values, but a fluid matrix of probabilities that crystallizes only upon contact. To understand why this is the case, we have to bypass the popular metaphors and look directly at the mathematical engine that drives the theory. At the very bottom of every isolated quantum system, be it a single traveling photon, a lone electron orbiting a nucleus, or a meticulously shielded cluster of atoms, lies a mathematical entity known as the wave function. The wave function is not a physical wave undulating through space like a ripple across a pond. Instead, it is an abstract mathematical description that maps out a complete landscape of possibilities. It does not dictate what will happen. It calculates the precise probability distribution of what could happen if you were to look. If a particle has the freedom to be in multiple places or possess multiple orientations, the wave function holds all of these options simultaneously in a state known as a superposition. The true crisis of the theory arrives when an observation takes place. When a detector clicks or a photographic plate registers a hit, the spread of probabilities instantly vanishes, replaced by a single, sharp, undeniable data point. This sudden transformation is historically referred to as the wave function collapse. It represents an abrupt, discontinuous leap from a smear of potential realities to a solitary, concrete truth. What makes this collapse so deeply problematic is that it is entirely absent from the fundamental equation that dictates how quantum systems grow and change over time. The Schrödinger equation, which serves as the bedrock of quantum dynamics, describes a world that is smooth, continuous, and completely deterministic. When left to its own devices, the wave function evolves predictably, shifting from one fluid distribution of probabilities to another without any sudden jumps or fractures. Yet our human experience of the world is never a fluid distribution of probabilities. We never see a fraction of an electron here and a fraction there. We see the entire particle land at a specific coordinate on our instrument. This irreconcilable tension between the continuous, elegant evolution of the Schrödinger equation and the violent, localized certainty of our experimental outcomes is what physicists call the measurement problem. It stands as perhaps the most profound, unresolved conceptual puzzle in modern physics. For a century, as our experiments grew more refined and our calculations more precise, the measurement problem was not diluted or explained away. Instead, it was brought into even sharper relief, forcing us to abandon our favorite intellectual escape hatches. For decades after the birth of the theory, many physicists clung to a deeply comforting assumption that the wave function was merely a reflection of human ignorance. They argued that quantum mechanics was simply incomplete. Just as a meteorologist uses probabilities to predict the weather because they lack perfect knowledge of every air molecule in the atmosphere, it was assumed that the probabilistic nature of the quantum world was a temporary mask hiding a deeper classical certainty. This perspective suggested that a particle truly did possess a definite spin or a localized position all along, and that the wave function was just a convenient accounting tool we used until we could uncover the deeper rules. These hypothetical hidden parameters were appropriately dubbed hidden variable theories, promising a return to the comfortable determinism of Isaac Newton, where the universe could once again be viewed as an objective machine running on hidden but entirely real gears. That comfortable escape route was permanently boarded up in 1964 by the Northern Irish physicist John Bell. He realized that if these hidden variables genuinely existed, they would impose a strict mathematical limit on how tightly the behaviors of separated particles could be linked. Bell formulated a mathematical inequality that set a definitive ceiling on the correlations between measurement outcomes for pairs of entangled particles, provided that the universe conformed to two basic assumptions: locality and realism. Locality is the common sense principle that an action taken in one corner of the galaxy cannot instantaneously alter an event in another. Information cannot travel faster than light. Realism is the philosophical stance we have been examining, the idea that objects possess objective properties before they are measured. Bell's genius was showing that if both local realism were true, the universe could only produce correlations up to a specific numerical threshold. Quantum mechanics, however, boldly predicted that nature could comfortably smash right through that threshold. The race to test Bell's inequality in real-world laboratories became one of the most vital experimental sagas of the late 20th century. Beginning in the 1970s and culminating in the landmark experiments conducted by Alain Aspect in 1982, physicists built sophisticated apparatuses to measure pairs of entangled photons flying in opposite directions. As the experiments grew more rigorous, closing potential loopholes that could allow regular signals to pass between the detectors, the results emerged with absolute clarity. The universe routinely and dramatically violated Bell's inequality. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger for their definitive experimental work proving that these violations are real, robust, and beyond doubt. Because Bell's inequality is a mathematical certainty, its violation forces humanity into a profound philosophical corner. We are left with an inescapable conclusion. One of Bell's two founding assumptions about the nature of reality must be completely false. Either we live in a universe devoid of locality, meaning an observation of a particle in a lab in Paris can instantaneously dictate the state of its entangled partner on Mars, or we must completely surrender realism, accepting that particles do not possess definite qualities until we measure them. While a minority of physicists look for ways to preserve realism through highly non-local mechanisms, the vast majority of the scientific community has chosen to let realism go. At its most fundamental level, the universe is not made of solid, predetermined components. If the subatomic foundations of our world are so profoundly fluid, we must confront an obvious question. Why does the macroscopic world look so utterly solid? If the atoms inside a porcelain teacup are individually hovering in states of indefinite limbo, why doesn't the teacup itself dissolve into a hazy cloud of quantum potential? The answer to this mystery does not require a breakdown of quantum physics at large scales. Rather, it emerges from a phenomenon known as decoherence. An isolated particle can maintain its delicate state of quantum superposition because it has not interacted with anything that could reveal its status. However, a macroscopic object like a teacup is never truly isolated. It is constantly bombarded by an astronomical number of environmental actors: stray photons, drifting air molecules, and thermal vibrations. When a quantum system collides with its environment, its original state of superposition does not mysteriously vanish into thin air. Instead, the quantum correlations spread outwards, instantly entangling the particle with the trillions of surrounding atoms. As this web of entanglement expands into the environment, the distinct phase relationships that allow different quantum possibilities to interfere with one another become hopelessly scrambled and diffused across a colossal number of particles. To an observer looking at the object, the quantum interference effects become completely unmeasurable in practice. The system begins to look and act exactly like a classical object with definite properties, not because the quantum laws have stopped working, but because the environment has acted as a giant, continuous, and inescapable measuring apparatus. Crucially, while decoherence explains why we do not see tables and chairs existing in multiple places at once, it does not actually solve the deeper mystery of the measurement problem. It explains how a quantum smear transforms into an apparent classical probability, but it still fails to explain why one specific concrete outcome is selected over all the others when we look. To bridge this gap, physicists have spent a century constructing different interpretations of the mathematics, trying to make sense of what the theory implies about the true nature of existence. The most historically entrenched framework is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg in the formative years of the theory. The Copenhagen approach adopts a posture of radical pragmatism. It argues that the wave function is not an objective physical script describing a real, underlying reality. It is merely an intellectual tool designed to calculate the likelihood of experimental outcomes. According to Bohr, asking what an electron is doing between measurements is a fundamentally meaningless question. There is no quantum world underneath the apparatus. There is only a mathematical description that helps us connect one macroscopic observation to the next. While this strict operationalism successfully protects physicists from falling into endless philosophical paradoxes, it does so at a massive conceptual cost. It asks us to abandon the idea that science can describe an objective world independent of our observations. Frustrated by this refusal to describe reality, Hugh Everett III proposed a radical alternative in 1957 that has steadily gained traction among modern theoretical physicists: the many worlds interpretation. Everett suggested that we should take the Schrödinger equation completely at face value. If the equation never shows a wave function collapsing, then perhaps the collapse never actually occurs. Instead, when a measurement takes place and a system faces multiple potential outcomes, the universe splits. Every single possible path is realized, but in separate, non-communicating branches of a rapidly multiplying universal wave function. If you measure an electron's spin and find it pointing upward, there is another version of you, existing in an equally real parallel branch of reality, observing the exact same electron pointing downward. The many worlds interpretation offers a beautiful, mathematically pristine view of the cosmos, free of arbitrary collapses, but it forces us to accept a reality populated by an infinite number of diverging lives. raising profound and unresolved questions about the nature of personal identity and what probability even means in a cosmos where every possible event is guaranteed to happen. Yet another path is carved out by pilot wave theory, also known as Bohmian mechanics. This approach attempts to rescue both determinism and realism from the quantum wreckage by suggesting that particles do indeed possess precise, permanent positions at all times. However, these particles do not move blindly. They are guided through space by a physical wave function that acts as a literal pilot wave. The apparent randomness we observe in our laboratories is not a fundamental property of nature, but a reflection of our unavoidable ignorance regarding the exact initial coordinates of the particles. The catch, however, is that to match the predictions of quantum mechanics, the pilot wave must be explicitly non-local. It must react instantaneously to changes anywhere in the cosmos, carrying influences across vast distances in total defiance of the localized spirit of Einstein's relativity. Because all three of these interpretations produce the exact same experimental predictions, they are currently impossible to distinguish in a laboratory, leaving the choice between them a matter of deep philosophical debate. For the bulk of the 20th century, these profound conceptual disagreements felt safely quarantined within the realm of the incredibly small. The consensus was that quantum mechanics ruled the domain of isolated subatomic particles, while classical physics maintained absolute authority over the macroscopic world we inhabit. The boundary between the two was assumed to be an unbreachable wall dictated by scale. However, that comfortable boundary has been utterly demolished by modern experimental physics. We now know that quantum mechanics does not care about the size of an object. It only cares about how well that object is isolated from its environment. This monumental shift in our understanding of reality was underscored by the awarding of the 2025 Nobel Prize in Physics to John Clark, Michel Devoret, and John Martinis. Their pioneering work demonstrated that it is possible to coax entirely macroscopic electrical circuits into behaving like single, coherent quantum objects. These devices are not microscopic anomalies hidden inside an atomic lattice. They are tangible, engineered structures fabricated on silicon chips that you can literally hold between your fingers. Yet, when these circuits are cooled to temperatures hovering just a fraction of a degree above absolute zero, they begin to violate the laws of classical electricity in spectacular fashion. They tunnel through seemingly impassable energy barriers, display sharply quantized energy levels, and enter into macroscopically distinct superpositions that violate Bell's inequalities with the same flawless fidelity as a lone pair of photons. The secret that unlocks this macroscopic quantum behavior is superconductivity. When specific metals are chilled to extreme temperatures, typically below minus 273.115 degrees Celsius, the thermal chaos that normally causes electrical resistance completely freezes out. Under these conditions, electrons no longer scurry through the material as individual chaotic entities bumping into impurities. Instead, they pair up into states called Cooper pairs, named after the physicist Leon Cooper, who cracked the mechanism in 1956. These pairs merge into a singular, vast quantum condensate that moves through the entire circuit as a unified front. The entire macro-scale electrical current becomes described by a solitary wave function with a unified quantum phase. By utilizing these superconducting currents, physicists can engineer artificial atoms. Just as an electron trapped inside a hydrogen atom can only occupy specific quantized energy levels, a superconducting circuit can be designed to possess discrete states of energy. Scientists can use carefully timed microwave pulses to drive these macroscopic currents into superpositions, forcing a circuit to simultaneously harbor two distinct energy states at once. This exquisite level of control is what enabled the rapid rise of modern quantum computing architectures. In 2019, a research team utilizing a superconducting quantum processor named Sycamore announced they had executed a highly specialized calculation in roughly 200 seconds, a task they calculated would tie up the world's most powerful classical supercomputer for 10,000 years. Though classical computer scientists quickly optimized their own algorithms to narrow the performance gap, the demonstration solidified a profound truth. Human beings can now engineer macroscopic systems that leverage the raw, non classical probabilities of the quantum world to manipulate information in ways no regular computer ever could. The success of these macroscopic experiments has fundamentally reshaped our view of the cosmos by revealing that the transition from the quantum world to the classical world is a continuous spectrum rather than a sudden, magical line in the sand. There is no critical mass or specific size at which the laws of nature abruptly rewrite themselves. The universe is quantum all the way up. The only reason a baseball behaves classically, while an electron behaves quantum mechanically, is that the baseball is hopelessly entangled with its warm, noisy environment. If you can take a large, multi-atom device, shield it from electromagnetic interference, and cool it until its thermal interactions drop to near zero, you can slide that macroscopic object across the spectrum, forcing it to reveal the same underlying indefiniteness that defines the subatomic realm. As physicists pushed deeper into the mathematical framework that makes this engineering possible, they encountered another unsettling realization concerning the language the universe uses to write its laws: the mandatory role of complex numbers. In classical physics, complex numbers, numbers that contain both a real part and an imaginary component, multiplied the square root of -1, are treated as a brilliant mathematical luxury. They are highly efficient tools for tracking things that cycle and oscillate, like alternating electrical currents or sound waves, because they elegantly bundle amplitude and phase together. However, in classical physics, you can always choose to throw away the complex notation and rewrite the entire system using standard pairs of real numbers without losing a single shred of physical insight. For nearly a century, it was widely assumed that the complex numbers appearing inside the quantum wave function were similarly expendable, a convenient shorthand that could eventually be purged from a complete description of reality. That long-held assumption was put to a definitive test in 2022. A research team led by Mingcheng Chen and Chaoyang Liu at the University of Science and Technology of China, alongside an international group of collaborators, executed an experiment explicitly designed to see if a version of quantum mechanics stripped of imaginary numbers could accurately predict the behavior of nature. By measuring the complex correlations between networks of photons, they looked for specific quantum interference patterns that could theoretically distinguish a standard complex wave function from a real-valued alternative. The results were clear and unequivocal. The real-valued alternative theory failed catastrophically to replicate the data, while the standard complex-valued predictions of quantum mechanics were validated to an overwhelming degree of statistical certainty. The imaginary unit is not a human cheat code or a mathematical shortcut. It is a physical necessity woven directly into the fabric of natural law. This structural requirement highlights the absolute centrality of quantum interference. When a system exists in a superposition, the different potential realities do not just coexist peacefully. Their complex phases interact dynamically. Depending on the alignment of these phases, the possibilities can experience constructive interference, making an outcome highly likely, or destructive interference, completely canceling the probability of an outcome out entirely. This is famously illustrated by the classic double-slit experiment, where individual particles fired at a barrier with two openings create a wave-like interference pattern on a detector screen behind it. A classical particle would have to choose one path or the other, making an interference pattern impossible. The quantum particle, however, travels via a complex wave function that senses both pathways simultaneously. The 2022 experiment demonstrated that this complex phase structure cannot be translated into a purely real-valued language without losing the very interference effects that dictate the behavior of our physical world. This realization that abstract mathematical constructs like complex phases are physically active components of the universe opens the door to a even more radical line of thought, the idea that the entire universe is fundamentally made of information. In the late 20th century, the legendary theoretical physicist John Archibald Wheeler distilled this concept into a potent three-word phrase: it from bit. Wheeler proposed that every physical object, every force, and every coordinate in spacetime is ultimately an emergent phenomenon arising from the answers to binary yes or no questions. In this view, matter and energy are not the primary ingredients of reality. They are secondary structures built upon a foundational bedrock of pure quantum information. While the it from bit philosophy remains a subject of intense conceptual exploration rather than an established consensus, the perspective that information is a tangible, physically real commodity has yielded immense practical insights. The most concrete manifestation of this idea comes from the work of Rolf Landauer in 1961. Landauer looked at the thermodynamics of computing and discovered a profound asymmetry. While reading or processing information can theoretically be done without spending any energy, the act of erasing information carries an inescapable physical cost. When you clear a bit of memory, resetting it from an uncertain state of ones and zeros back to a clean state of zero, you are decreasing the thermodynamic entropy of that memory register. Because the second law of thermodynamics strictly forbids the total entropy of an isolated system from ever decreasing, that lost entropy must be cast out into the environment as heat. Landauer calculated the absolute minimum amount of heat generated by the erasure of a single bit of information, a threshold now known as the Landauer limit. It is defined precisely as the temperature of the system multiplied by Boltzmann's constant and the natural logarithm of 2. At standard room temperature, this amounts to a vanishingly small quantity. For most of modern computing history, this limit was purely academic, as our silicon chips were so inefficient that they wasted orders of magnitude more energy than Landauer's threshold. But as microprocessors continue to shrink toward the atomic scale, their operational energy profiles are beginning to approach this fundamental baseline. Landauer's limit has been verified in modern physics labs, demonstrating an ironclad measurable bridge between a purely abstract, logical concept like information and a raw physical quantity like heat. Information is not a figment of human thought. It is a fundamental property of the physical world that leaves a thermal footprint. This profound realization that information cannot be truly destroyed or ignored has set the stage for one of the most famous crises in modern physics, the black hole information paradox. Black holes are the ultimate monsters of general relativity, regions of spacetime where mass is packed so tightly that the resulting gravitational pull prevents anything, even light, from escaping once it crosses the invisible boundary known as the event horizon. For a long time, it was believed that black holes were cosmic dead ends, frozen objects that simply swallowed matter and locked it away forever. That view was shattered in 1974 when Stephen Hawking introduced quantum mechanics into the vicinity of the event horizon. Hawking demonstrated that the intense gravitational fields near the horizon could spontaneously generate pairs of virtual particles out of the quantum vacuum. Occasionally, one particle would fall into the black hole while its partner escaped out into space as thermal radiation. This phenomenon, now universally known as Hawking radiation, meant that black holes were slowly leaking mass. Over vast cosmological epochs, a black hole would gradually shrink and eventually evaporate out of existence in a final silent puff of energy. The paradox that keeps theoretical physicists awake at night stems from the precise nature of Hawking's radiation. According to his original semi-classical calculations, the radiation escaping from the black hole is completely thermal and entirely featureless. It carries absolutely no memory of the material that formed the black hole in the first place. If you were to build a black hole out of valuable books containing the sum of human knowledge and another identical black hole out of raw hydrogen gas, both would emit completely indistinguishable Hawking radiation. When both black holes finally evaporate into nothingness, all the information about the books and the gas appears to be utterly erased from the universe. This creates a catastrophic conflict with the absolute bedrock of quantum mechanics, the principle of unitarity. In quantum theory, the mathematical operators that govern the evolution of a system are unitary, meaning they preserve probabilities and are completely, fundamentally reversible. If you know the final, complete quantum state of an isolated system, you must always be able to run the equations backward to perfectly reconstruct its past. Information can be scrambled, heated, and scattered into an unreadable mess, but it can never be completely wiped from the cosmic ledger. If Hawking's original calculation is right, and a evaporating black hole truly destroys information, then the core equations of quantum mechanics are broken. If quantum mechanics is right and information is preserved, then general relativity's description of the event horizon must be missing something monumental. The effort to resolve this paradox has become the primary testing ground for any candidate theory seeking to unify quantum mechanics with general relativity. A profound breakthrough arrived in the early 2020s through the collaborative work of theorists including Ahmed Almhiri, Netta Engelhard, Donald Merolf, and Henry Maxfield. Working within the highly specialized mathematical framework of the holographic principle and the anti-de Sitter conformal field theory, ADS-CFT correspondence, they re-examined the entropy of the radiation leaking out of an evaporating black hole by employing advanced gravitational path integral techniques to map the complex quantum geometries inside the black hole. They discovered something extraordinary. The information is not destroyed. Their calculations revealed that the entropy of the Hawking radiation follows a distinct curve known as the Page curve. For the first half of the black hole's long lifetime, the entropy of the emitted radiation steadily rises, looking exactly like the random thermal smear that Hawking predicted. But at a critical juncture, known as the Page time, the trend reverses. The entropy begins to decline steadily as the black hole continues to shrink. This decline means that the radiation escaping during the latter half of the evaporation process is subtly, exquisitely linked to the radiation that escaped at the beginning. The information is not wiped out. It is deeply encoded within the complex, non-local quantum correlations between the emitted photons. While extracting that information from the radiation would be an almost impossible feat for an observer outside, the mathematics proves that the evolution remains entirely unitary. Quantum mechanics holds its ground. Information is truly indestructible. The hunt to understand exactly how this information escapes has pulled physicists into the deepest question of all: what are space and time made of? In Albert Einstein's general relativity, space-time is viewed as a smooth, continuous, four-dimensional fabric that bends and warps under the weight of stars and planets, creating the illusion of gravity. Quantum mechanics, on the other hand, treats space-time as a completely rigid, fixed background stage upon which quantum fields play out their dances. These two descriptions are structurally incompatible, and attempting to force them together using standard methods yields nonsensical equations riddled with uncontrollable infinities. To heal this rift, physicists have developed two primary competing research programs. The first, loop quantum gravity, proposes that the smooth fabric of Einstein's spacetime is an illusion born of scale. It suggests that if you could zoom in all the way down to the Planck length, an unimaginably minuscule scale, you would discover that space is not continuous at all. Instead, it is broken up into discrete quantized packets, woven together out of a dense network of quantum loops. In this framework, spacetime is highly granular, and the smooth geometry we experience is merely the collective, macroscopic average of countless microscopic loops interacting at the smallest scales. The second major framework, string theory, approaches the problem by replacing the concept of zero-dimensional point particles with one-dimensional vibrating objects called strings. According to string theory, every fundamental particle in the universe, whether it is a quark, an electron, or a photon, is actually the exact same type of fundamental string vibrating at a different frequency. Because string theory naturally includes a vibrational mode that corresponds perfectly to the graviton, the hypothetical quantum particle of gravity, it inherently unifies general relativity with the quantum forces. The catch is that the mathematics of string theory only works if the universe possesses extra spatial dimensions beyond the three we can see, forcing theorists to conclude that these extra dimensions must be tightly curled up at scales far too small for our current particle colliders to detect. While neither loop quantum gravity nor string theory has managed to produce a definitive, distinct prediction that can be verified in a modern laboratory, the intense mathematical cross-pollination between them has revealed a stunning new insight into the nature of reality, the idea that space-time geometry is generated by quantum entanglement. This concept traces its roots back to 1997 when Juan Maldacena discovered the DSCFT correspondence, demonstrating that a gravity-free quantum universe living on the boundary of a specific space-time region is mathematically equivalent to a higher dimensional universe containing gravity operating on the inside, or the bulk. Building directly upon this holographic foundation, the physicist Mark van Ramsdonk published a pivotal analysis in 2010 showing that if you mathematically reduce the quantum entanglement between the particles on the boundary theory to zero, the smooth geometric fabric of the interior space-time literally tears itself apart into disconnected fragments. The implications of this are breathtaking. It means that the smooth space-time coordinates we use to navigate our daily lives, the very concept of distance, geometry, and time, are not fundamental aspects of the universe. They are emergent illusions woven together by the unseen threads of quantum entanglement. When you trust quantum mechanics completely, the world transforms from a collection of solid things sitting in a pre-existing room into a deeply interconnected web of information where properties are born from interactions, where complex numbers are a physical law, and where the very fabric of space and time is stitched together by the weirdness of quantum correlations. We are not passive spectators looking at an objective clockwork box. We are participatory components of a universe that is still deciding what it wants to be. This emergent picture of a geometry stitched together by entanglement is not merely a radical mathematical trick. It is the starting point for an entirely new way of conceiving how the universe hangs together. If space-time itself is synthesized from quantum correlations, then the old way of thinking about gravity as a force that pulls massive objects through a pre-existing arena is fundamentally backwards. Gravity is not something that happens in space. Gravity is the macroscopic signature of quantum information processing occurring at the most fundamental level. When you drop an apple, it does not fall because it is being pulled by invisible gravitational lines of force across a smooth void. It falls because the density of quantum entanglement in the space-time fabric beneath it is subtly different from the density of entanglement above it, causing the apple's wave function to slide along a gradient of quantum complexity. To grasp how deeply this upends our classical assumptions, we must look at how this perspective reframes the concept of distance. In our ordinary everyday lives, distance is the ultimate separator. If two objects are separated by a vast distance, say a light year of empty space, we assume they are physically isolated from one another. To send a signal from one to the other takes time, limited by the speed of light. This is the very definition of locality. But if space-time is emergent from entanglement, then distance is not a fundamental barrier at all. It is a secondary property. Two particles that appear to be separated by vast expanses of empty space in our three-dimensional world can remain directly, intimately linked in the underlying quantum description. They are, in a very real sense, right next to each other in the network of information that generates the space-time fabric. The apparent distance between them is an illusion created by the way we, as macroscopic observers, perceive the entangled network. This realization has led to one of the most provocative proposals in modern theoretical physics. Proposed by Juan Maldacena and Leonard Susskind in 2013, this conjecture links two seemingly completely different papers written by Albert Einstein and his collaborators in 1935. The first paper, written with Boris Podolsky and Nathan Rosen, EPR, described the phenomenon of quantum entanglement, what Einstein famously and skeptically called spooky action at a distance. The second paper, written with Rosen, ER, described what we now call a wormhole, a shortcut through the fabric of spacetime connecting two distant regions via a throat, mathematically known as an Einstein-Rosen bridge. For nearly 80 years, these two papers were treated as completely unrelated contributions to physics. One was a critique of quantum mechanics, the other a mathematical curiosity of general relativity. But it suggests they are actually two different ways of describing the exact same physical phenomenon. The conjecture asserts that if you have two quantum mechanically entangled particles, an EPR pair, they are physically connected by a tiny microscopic wormhole, an ER bridge, in the underlying geometry of the universe. If you have a large number of entangled particles, their collective wormhole connections stitch together to form a smooth, macroscopic corridor of space-time. Entanglement is the glue that holds the universe together. Without it, space-time would instantly dissolve into a chaotic, disconnected dust of individual quantum events, with no here or there to connect them. If this sounds like science fiction, it is only because we are still accustomed to looking at the universe through the lens of classical realism. But as our experiments continue to push the boundaries of what can be engineered, the line between theoretical speculation and practical reality is becoming vanishingly thin. This is nowhere more apparent than in the field of quantum teleportation. First proposed theoretically in 1993 and demonstrated experimentally shortly thereafter, quantum teleportation is not the science fiction dream of physically beaming a person from one location to another. Instead, it is something far more profound, the instantaneous transfer of an unknown quantum state across space using the power of entanglement and classical communication. In a standard quantum teleportation protocol, two parties, conventionally called Alice and Bob, share a pair of entangled particles. Alice also possesses a third particle whose quantum state is completely unknown to her. By performing a specific joint measurement on her half of the entangled pair and the unknown particle, Alice forces her particles into a collective state. Because of the non-local correlation shared with Bob's particle, this measurement instantaneously alters the state of Bob's particle, transferring a portion of the quantum information to him. To complete the process, Alice must send the classical results of her measurement to Bob via a conventional channel, such as a radio wave or a fiber optic cable. Once Bob receives this classical data, he can perform a precise physical rotation on his particle, reconstructing the exact original unknown quantum state that Alice started with. What makes quantum teleportation so philosophically striking is that during the measurement process, the original quantum state in Alice's possession is completely destroyed. This is not a technical limitation. It is a strict mathematical law known as the no-cloning theorem. You cannot copy an unknown quantum state. You can only transfer it. The information does not travel through the space between Alice and Bob as a physical signal. Instead, it disappears from one location and reappears at the other, guided by the non-local link of entanglement. If you view the process through the lens, the quantum state has literally traveled through a microscopic wormhole connecting Alice and Bob's systems, emerging on the other side once Bob applies the correct classical key to unlock it. This deep connection between information, geometry, and quantum mechanics has forced a radical reevaluation of the role of the observer in physics. In the classical worldview, the observer is a passive chronicler of events, sitting safely outside the system, recording data with no more impact on the outcome than a spectator watching a play. But in a quantum universe where properties are undefined prior to measurement, and where space-time itself emerges from entanglement, the observer is an active participant in the construction of reality. Every measurement you perform, every observation you make, is an act of creation. It forces a system that was hovering in a cloud of infinite possibilities to collapse into a single concrete state, generating new entanglement, altering the local geometry, and leaving an indelible thermal footprint on the thermodynamic ledger of the cosmos. This participatory nature of the universe is what led the physicist John Wheeler to suggest that we should replace the word observer with the word participator. In Wheeler's view, the universe is a self-referential system that brings itself into existence through the act of observing itself. He illustrated this with his famous U diagram, where one arm of the giant letter U represents the early universe, evolving over billions of years, while the other arm represents the emergence of conscious observers who look back at the beginning, closing the loop and giving the early universe a definite, concrete reality. Without this act of observation, the universe would remain a giant, uncollapsed wave function, a gargantuan cloud of potential realities with no one to experience them, and therefore no definite existence. This radical perspective is not without its critics, even among those who fully accept the mathematical validity of quantum mechanics. The primary objection is that it appears to elevate consciousness or human agency to a fundamental status in physics, a move that many scientists find deeply uncomfortable. It seems to resurrect the ghost of anthropocentrism, suggesting that the universe somehow needs us to exist. To avoid this conclusion, many modern physicists prefer to define measurement and observation in purely physical, non-conscious terms. A measurement is not an act of human awareness. It is simply any interaction between a quantum system and a macroscopic system that is large enough to cause decoherence. When an electron collides with a molecule of gas in interstellar space, a measurement has occurred and the wave function collapses, regardless of whether a human scientist is there to record the event. However, even this objective view of decoherence does not fully escape the weirdness of the measurement problem. It simply pushes the mystery one step further back. If the universe is quantum all the way up, then the gas molecule, the interstellar dust, and the entire galaxy are themselves described by a vast, incredibly complex wave function. If there is no external observer to collapse this universal wave function, then the entire cosmos must exist in a colossal, hyper-entangled superposition of all possible histories. Every path the universe could have taken since the Big Bang is still occurring, running in parallel branches of an unimaginably vast multi-world reality. In this view, we do not collapse the wave function. We are simply riding one particular branch of it, completely oblivious to the infinite other versions of ourselves who are currently experiencing different outcomes on sister branches of the cosmic tree. The tension between these different interpretations is not just an academic debate. It has profound implications for how we search for a unified theory of physics. If the Copenhagen interpretation is correct, and the wave function is merely an intellectual tool rather than a physical reality, then we may have to accept that there are fundamental limits to what science can say about the universe. We may have to resign ourselves to a world where we can calculate probabilities with flawless precision, but can never know what is actually happening behind the scenes. If the many worlds interpretation is correct, we must accept a dizzying, infinite multiverse that challenges our most basic notions of identity, morality, and probability. If pilot wave theory is correct, we must accept a universe where non-local, faster-than-light influences are constantly whispering across the cosmos, coordinating the movements of every particle in a deterministic dance that mocks our belief in free will. As we stand on the frontier of this research, the traditional boundaries that once separated physics, philosophy, and computer science are completely dissolving. The study of quantum information has shown that the laws of computation are not abstract mathematical truths, but are directly dictated by the laws of physics. A classical computer running on the binary logic of ones and zeros is a reflection of a classical realist worldview. A quantum computer running on qubits that can exist in superpositions of 0 and 1 is a direct exploitation of the true, fluid nature of the universe. By building these machines, we are not just creating faster tools for calculation, we are building physical systems that probe the very boundaries of reality, testing the limits of decoherence and forcing the universe to reveal how it handles information at a scale never before seen in natural history. This technological push is driving us toward a future where we may finally be able to answer some of the deepest questions about the nature of space and time. Already, researchers are using quantum computers to simulate toy models of black holes, testing the dynamics of Hawking radiation and the holographic principle in the safety of a laboratory chip. By watching how information scrambles and unscrambles across these artificial systems, we are gaining concrete insights into how gravity might emerge from quantum networks, providing a bridge between the mathematics of string theory and the experimental reality of our labs. We are no longer just theorizing about the quantum origin of space-time. We are beginning to build it, gate by gate, qubit by qubit. The journey that began in 1925 with a handful of physicists trying to make sense of the strange behavior of light and atoms has led us to a place where we must surrender our most cherished assumptions about the world we inhabit. We must let go of the idea that things have definite properties when we are not looking. We must accept that the universe is not a collection of solid, independent objects, but a dynamic, participatory network of information. We must face the reality that space and time are not the permanent, unshakable foundations of existence, but are emergent properties woven from the delicate threads of quantum entanglement. It is a world that is stranger, more fluid, and far more deeply interconnected than our ancestors could have ever imagined. The instinct to push back against this is understandable. It is the voice of our macroscopic evolutionary heritage, pleading for a world of simple, predictable permanence. But the data does not care about our instincts. The more carefully we probe the universe, the more clearly it whispers its true nature to us. A nature not of hard edges and predetermined paths, but of infinite possibilities waiting for an interaction to bring them into the light of day. To trust quantum physics is to accept that we are not just observers of this magnificent, unfolding reality. We are the very process through which the universe discovers itself. This self-discovery is not a gentle, passive process. It is a violent, transformative event that reverberates across the entire structure of the cosmos. Every time a quantum interaction occurs, a ripple of decoherence propagates outwards, rewriting the local relationships between particles, generating fresh entanglement, and redefining the local geometry of space-time. It is as if the universe is a giant, unfinished tapestry, and every observation is a stitch that pulls the threads tighter, defining a shape here, a color there, but leaving the rest of the canvas in a state of beautiful, shimmering potential. This view of a participatory universe completely redefines what we mean by a physical law. In the classical Newtonian view, physical laws are absolute, immutable rules carved into the bedrock of existence. They are the external constraints that dictate how matter must behave. But in a quantum universe where information is fundamental and reality is emergent, the laws of physics may be more akin to software running on a cosmic operating system. They are the rules that govern how information is processed, conserved, and transformed. The constancy of the speed of light, the conservation of energy, the second law of thermodynamics. These may not be arbitrary, brute facts of existence, but the necessary system requirements for a universe that is mathematically consistent and capable of generating emergent, macroscopic structures like stars, planets, and conscious minds. If this information-centric view of physics is correct, it suggests that the ultimate limit on our ability to understand the universe is not a limit of technology, but a limit of computation. The universe is, in a very real sense, a computer calculating its own future in real time. It does not use shortcut algorithms. It runs the simulation at a scale of 1-to-1, using every particle, every wave function, and every quantum correlation to compute the next state of existence. Our science is the attempt to reverse engineer this cosmic software, to find the compressed formulas and mathematical models that allow us to predict the outcome of the calculation before the universe itself has finished running it. This is why the discovery of macroscopic quantum systems, like the superconducting circuits that earned the 2025 Nobel Prize, is such a monumental milestone in human history. For the first time, we have managed to build our own localized subroutines within this cosmic computer. We have managed to isolate macroscopic quantities of matter from the ambient noise of the universe, allowing us to write our own quantum code and run our own non-classical calculations. We are no longer just passive bits of data being processed by the universal machine. We are beginning to write our own programs, manipulating the fundamental substrate of reality to explore regions of the mathematical landscape that have never been accessed since the Big Bang. The consequences of this transition are impossible to predict. We are standing at the very beginning of the quantum information age, a transition they prove to be far more profound than the industrial or digital revolutions that preceded it. Those earlier revolutions were about manipulating matter and classical information, shaping iron, burning coal, and routing electrical currents through binary gates. The quantum information revolution is about manipulating reality itself. It is about learning to control the fundamental processes of superposition, entanglement, and decoherence that generate the macroscopic world. As we develop this capacity, we may find that the distinction between artificial and natural begins to blur. If we can engineer macroscopic systems that display perfect quantum coherence, if we can build materials whose properties are dictated by designed entanglement structures, we will be creating states of matter that do not exist anywhere else in the natural universe. We will be expanding the vocabulary of reality, writing new physical possibilities into the cosmic script. And yet, as we push further into this engineered quantum future, the ancient philosophical questions that have haunted the theory since its birth remain as sharp and urgent as ever. The measurement problem has not been solved by our ability to build quantum computers. If anything, it has been brought into even sharper focus. As our qubits grow more numerous and our quantum processors more complex, we are forced to confront the question of where the quantum world ends and our classical experience begins with unprecedented precision. If a quantum computer performs a calculation involving a massive superposition of states and then writes the final classical result to a hard drive, when did the wave function collapse? Was it when the individual qubits interacted with the readout resonators? Was it when the electrical signal traveled along the coaxial cables to the classical control computer? Was it when the data was displayed on a scientist's monitor? Or does the entire system, the quantum computer, the laboratory, the scientist, and the surrounding city, remain in a colossal uncollapsed superposition until it is observed by some external cosmic participator? The fact that we still do not know the answer to this question, even as we build machines that exploit the very mechanics of the collapse, is a testament to the profound depth of the mystery. It is a reminder that physics is not a closed book, but an ongoing adventure that is constantly forcing us to revise our understanding of what it means to exist. The more we learn, the more we are forced to accept that the universe is not a passive, objective machine, but a dynamic, self-referential system of incredible subtlety and beauty. To trust quantum physics is to embrace this uncertainty. It is to accept that the world is not a static collection of facts waiting to be discovered, but a fluid unfolding process in which we are deeply and inextricably entangled. It is to realize that when we look out into the depths of space or down into the heart of the atom, we are not looking at something separate from ourselves. We are looking at the universe reflecting upon its own nature, using the medium of human consciousness to bring its own infinite possibilities into sharp, beautiful, and enduring focus. This process of reflection is not confined to the sterile environment of the physics lab. It is a fundamental feature of the universe's history. From the moment of the Big Bang, the cosmos has been on a trajectory of increasing complexity, moving from a smooth, hot plasma of identical particles to a rich, diverse landscape of galaxies, stars, heavy elements, organic molecules, and eventually living systems. At every stage of this cosmic evolution, the emergence of new levels of structure has been accompanied by new ways of processing and storing information. In the early universe, information was simple and thermodynamic, encoded in the distribution of matter and radiation in a rapidly expanding space-time. As stars formed and fused light elements into heavy ones, the physical vocabulary of the universe expanded, allowing for the creation of complex chemical bonds. With the rise of life on Earth, information took on a new semantic character, encoded in the digital sequences of DNA and RNA, allowing organisms to store a record of evolutionary history and adapt to their environments. And with the emergence of conscious minds, information became subjective and self-aware, allowing the universe to construct internal models of itself, to contemplate its own past, and to deliberate over its own future. Seen from this perspective, the development of quantum mechanics and the rise of quantum information technology are not accidental detours in human history. They are the natural continuation of this cosmological trend. They represent the moment when the universe, having evolved conscious observers capable of reverse engineering its laws, begins to take direct control of its own quantum substrate. We are the universe learning to program itself. This realization carries a profound sense of responsibility. If we are not passive observers, but active participators in the construction of reality, then our choices, our observations, and our technologies are not isolated events occurring on a tiny rock in a vast, indifferent void. They are cosmological events shaping the local structure of the quantum web and contributing to the ongoing evolution of the universal wave function. The information we generate, the systems we build, and the questions we choose to ask are the active ingredients that determine which branch of the infinite multiverse we will ultimately inhabit. As we move forward into this uncharted territory, we must resist the temptation to fall back into the comfortable reductionist thinking of the past. We must resist the urge to treat the quantum world as a mere curiosity, a strange subatomic domain that can be safely ignored in our daily lives. The lessons of the past century are clear. The quantum world is the only world there is. The classical solidity of our everyday experience is not a fundamental truth, but a highly specialized, emergent illusion generated by the complex dynamics of decoherence. To live in a quantum universe is to live in a world of profound connection. It is to know that at the deepest level, we are not separate, isolated individuals bumping into each other in a cold, Newtonian void. We are entangled components of a single, continuous quantum system, sharing a history that stretches back to the Big Bang and a future that is still being actively calculated. The apparent boundaries that separate us, our skin, our languages, our distances, are the products of decoherence, the macroscopic noise that masks the underlying unity of the cosmic wave function. By learning to quiet that noise, by building systems that can maintain their quantum coherence, and exploring the deep, non-local correlations that link distant parts of the cosmos, we are not just doing physics. We are practicing a form of cosmic archaeology, uncovering the ancient, primordial threads of connection that have held the universe together since the beginning of time. We are learning to read the language of phase and amplitude, of superposition and interference. It is a language that is difficult to learn, written in the demanding grammar of complex numbers and high-dimensional Hilbert spaces. It is a language that challenges our common sense, mocks our evolutionary instincts, and demands a level of intellectual humility that is rare in human history. But it is the native language of the cosmos, the script in which the true story of reality is being written. As we continue to decipher this script, we will undoubtedly encounter new paradoxes, new crises, and new revelations that will force us to tear up our existing models and start again. The measurement problem may remain unsolved for another century, or it may be resolved tomorrow by a breakthrough that renders all our current interpretations obsolete. The black hole information paradox may lead us to a completely new theory of quantum gravity, or it may reveal that gravity itself is just the tip of a much larger, more mysterious cosmological iceberg. But whatever discoveries await us on the horizon, we can be certain of one thing. The universe will continue to surprise us. It will not conform to our simple, classical expectations. It will not behave like a collection of predetermined objects waiting to be found. It will remain a fluid, dynamic, and participatory system whose values are genuinely undetermined until the interaction that determines them occurs. And in that very indeterminacy lies our greatest hope and our deepest freedom. In a universe where nothing is completely decided in advance, where the future is not a fixed track, but a branching tree of infinite possibilities, our choices truly matter. Our observations are not predetermined scripts. They are active, creative acts that help shape the unfolding history of the cosmos. We are not prisoners of a mechanical clockwork machine. We are the co-authors of a living, breathing, and self-creating reality. To start trusting quantum physics is to step off the safe, solid shore of classical certainty and plunge into the deep, shimmering waters of the quantum ocean. It is a journey that requires courage, curiosity, and a willingness to let go of the comforting illusions of the past. But for those who are willing to make the leap, the reward is nothing less than a direct, unmediated encounter with the true, breathtaking majesty of the cosmos, a universe of infinite potential, bound together by the invisible threads of entanglement and waiting for us to look. This quantum ocean is not a silent, dark void. It is alive with the music of phase and interference, a symphony of possibilities that has been playing since the dawn of time. Every particle, every wave function, every entangled pair is a note in this cosmic score, contributing to a melody that is constantly evolving, constantly changing, and constantly searching for new ways to express itself. As we build our quantum computers, as we measure our superconducting circuits, and as we calculate the entropy of evaporating black holes, we are not just listening to this music. We are beginning to play along. We are adding our own voices to the choir, creating new harmonies and exploring new rhythms that have never been heard before. We are transforming the universe from a solo performance into a grand, participatory jam session where the boundary between the musician and the instrument is completely dissolved. It is a performance that is happening right now, in every atom of your body, in every light year of empty space, and in every parallel branch of the universal wave function. It is a performance that does not require a stage, because the stage itself is being created by the music. It is a performance that has no audience, because everyone is on stage, participating in the construction of the reality we share. And so, we must keep looking, keep measuring, and keep asking the deep, difficult questions that force the universe to make its choices. We must not shrink from the paradoxes, or run from the weirdness, or retreat into the safe, comfortable corners of classical realism. We must push forward with our math, our lasers, and our superconducting chips into the very heart of the quantum mystery. For it is only there, at the boundary, where indefiniteness gives way to definiteness, where the wave function collapses and reality crystallizes into being, that we can hope to find the true meaning of our existence. It is only there that we can begin to understand why we are here, what we are made of, and where we are going. It is only there, in the quiet, coherent spaces of the quantum world, that we can truly stand face to face with the ultimate, beautiful, and deeply strange nature of the universe we call home. This home is not a static building, but a living, breathing structure that is constantly remodeling itself in response to our presence. The walls are not made of solid stone, but of probability amplitudes. The floors are not anchored in the bedrock, but in the emergent geometry of entanglement, and the windows do not look out onto an independent landscape, but onto a mirror that reflects our own inquiring gaze. When you step out of the room does not simply wait for you in the dark. It hovers, a beautiful, uncollapsed cloud of potential configurations, waiting for the creak of your footstep or the click of the light switch to snap back into its familiar classical shape. It is a world that is intimately, exquisitely sensitive to your existence, a world that cares that you are there, because without you, it would not know how to be. To accept this is to experience a profound shift in perspective, a kind of cosmic homecoming. You are no longer an alien observer, dropped into a cold, indifferent world of pre-existing matter. You are a necessary, integral part of the cosmic machinery, a key player in the grand, unfolding story of creation. Your eyes are the instruments through which the universe sees its own beauty. Your mind is the laboratory in which it tests its own equations. And your technologies are the tools through which it explores its own infinite possibilities. As we look to the future, to the quantum networks that will soon span the globe, to the quantum sensors that will probe the deepest structures of the Earth and space, and to the quantum computers that will solve the grandest mysteries of chemistry, biology, and cosmology, we are not just looking at a technological revolution. We are looking at a species growing up, transitioning from a childhood of passive observation to an adulthood of active participation. It is a transition that will change everything, not in the way that a thermometer slightly warms the liquid it touches, but in a way that is far more fundamental. It will change our relationship with nature, our understanding of ourselves, and our place in the cosmic order. It will force us to rewrite our philosophies, our structures, and our dreams, aligning them with the true, fluid, and deeply interconnected reality that quantum physics has revealed. The journey is long, the terrain is strange, and the destination is completely unknown. But as we step forward into this quantum future, we can take comfort in the knowledge that we are not traveling alone. We are accompanied by the very laws of nature, by the elegant mathematics of the wave function, and by the deep, indestructible correlations of entanglement that connect us to every corner of the cosmos. The universe is waiting. The wave function of the future is smooth, continuous, and completely open, a vast spread of beautiful possibilities waiting for us to make our move. The next measurement is ours to perform. The next interaction is ours to choose. And in the very act of choosing, we will bring the next chapter of our reality into existence, creating a world that is richer, stranger, and more wondrous than anything that has ever gone before. To fully comprehend how profoundly this information theoretic view reshapes our understanding of the physical world, we must return to the historical crisis that shattered the clockwork universe of classical mechanics at the dawn of the 20th century. For over 200 years, the physics of Isaac Newton and James Clerk Maxwell reigned supreme. It was a physics of absolute continuity. Space was an empty, passive container. Time flowed uniformly and inexorably forward, and matter was composed of solid, localized particles that moved along smooth, deterministic trajectories. Waves were continuous disturbances propagating through physical media, and energy could be divided into infinitely small portions. This classical worldview was so elegant, so intuitive, and so successful at predicting the motions of planets and the behavior of steam engines that it was widely assumed the fundamental laws of nature were essentially complete. But as physicists began to probe the behavior of matter and light at the smallest scales, this picture of absolute continuity began to fracture. The first crack appeared in the study of blackbody radiation, the light emitted by a heated, idealized object. According to classical electromagnetism, a heated cavity should radiate energy across all frequencies, with the energy density increasing without limit as the frequency of the radiation increased. This mathematical prediction, which became known as the ultraviolet catastrophe, was a catastrophic failure of classical theory. It predicted that any warm object, even a simple household oven or a glowing coal, should instantly radiate away an infinite amount of energy in the ultraviolet and high-frequency spectrum, blinding anyone nearby and violating the conservation of energy. The crisis was resolved in 1900 by the German physicist Max Planck, who introduced a desperate mathematical trick to make the equations match the experimental data. Planck proposed that the walls of the heated cavity did not absorb and emit electromagnetic energy continuously. Instead, they exchanged energy only in discrete, indivisible packets, which he called quanta. The energy of each packet was directly proportional to the frequency of the radiation, multiplied by a tiny new constant of nature, now known as Planck's constant. At the time, Planck did not believe these quanta were physically real. He viewed them as a temporary mathematical convenience, a formal patch to keep his equations from running off to infinity. It was Albert Einstein who took Planck's quanta seriously. In 1905, Einstein used the concept of quantized energy to explain the photoelectric effect, the phenomenon where light shining on a metal surface knocks electrons free, generating an electrical current. Classical physics predicted that the energy of the ejected electrons should depend on the brightness of the light, as a brighter, more intense wave should carry more force to shake the electrons loose. But experiments showed the opposite. The energy of the electrons depended solely on the frequency or color of the light, while the brightness merely determined the number of electrons ejected. Einstein realized that light itself is not a continuous wave, but is composed of localized packets of energy, which we now call photons. When a photon strikes an electron inside the metal, it delivers its energy in an all-or-nothing event. If the photon's frequency is too low, it lacks the energy to free the electron, no matter how many photons rain down upon the surface. This was the birth of wave-particle duality, the foundational paradox of quantum mechanics. Light, which Maxwell had proved was a continuous wave, was also behaving like a stream of discrete particles. Soon after, the French physicist Louis de Broglie turned this concept on its head, proposing that if light waves could behave like particles, then material particles like electrons must also behave like waves. De Broglie's hypothesis was quickly confirmed by experiments showing that electrons fired through a crystal lattice produced the exact same diffraction and interference patterns as X-rays. The solid, localized corpuscles of Newtonian matter had dissolved into waves of probability. To mathematically describe these matter waves, the Austrian physicist Erwin Schrödinger formulated his famous wave equation in 1926. The Schrödinger equation was a triumph of mathematical physics, providing a precise, deterministic framework for calculating how the quantum state of a system evolves over time. But it also introduced a deep conceptual puzzle. What exactly was waving? In a water wave, it is the molecules of water that move up and down. In a sound wave, it is the pressure of the air. In an electromagnetic wave, it is the strength of the electric and magnetic fields. But the wave function of quantum mechanics, denoted by the Greek letter psi, was not a wave of any physical substance. The answer was provided by the German physicist Max Born, who realized that the wave function is a wave of probability. The value of the wave function at any given point in space is a complex number containing both a real part and an imaginary part. On its own, this complex amplitude has no direct physical meaning, but if you take the square of its magnitude, you obtain a real number that represents the probability density of finding the particle at that location if a measurement is performed. This interpretation, which earned Born the Nobel Prize, represented a radical departure from classical determinism. In quantum mechanics, we can no longer predict where a particle will go. We can only calculate the probability of finding it in various places. To understand how this probability is structured, we must look at the mathematical home of the wave function, Hilbert space. In classical mechanics, the state of a particle is described by its position and momentum, which can be represented as coordinates in a simple, three-dimensional physical space. But in quantum mechanics, the state of a system is represented as a vector in an abstract, multidimensional, and often infinite-dimensional complex vector space, called a Hilbert space. Every possible configuration of the system corresponds to a distinct direction or axis in this space. When a system exists in a superposition, its state vector is not pointing along any single axis. Instead, it is pointing in a direction that is a linear combination of multiple axes. The physical properties of the system, such as its position, momentum, energy, or spin, are represented in this mathematical framework not by numbers, but by operators. An operator is a mathematical instruction that acts on a state vector, rotating it or stretching it within the Hilbert space. When we perform a measurement on a quantum system, we are applying the operator corresponding to that property to the system's state vector. The mathematics of Hilbert space dictates that the only possible outcomes of this measurement are the eigenvalues of the operator, the specific values for which the operator simply scales the state vector without changing its direction. The corresponding state vectors are called eigenstates. This mathematical structure has a profound physical implication known as Born's rule. When a measurement is performed, the state vector of the system is instantaneously projected or collapsed onto one of the eigenstates of the measuring operator. The probability of obtaining a specific eigenvalue is determined by the angle between the system's original state vector and the corresponding eigenstate in Hilbert space. If the state vector is close to a particular eigenstate, the probability of collapsing onto that state is high. If it is perpendicular, the probability is 0. This projection is what gives quantum mechanics its discontinuous random character. Before the measurement, the state vector evolved smoothly and deterministically according to the Schrödinger equation, rotating gracefully through the high-dimensional geometry of Hilbert space. But the act of measurement forces a sudden, irreversible jump, snapping the vector onto one of the measurement axes. This is the origin of the measurement problem. The mathematical formalism of quantum mechanics describes two completely different, incompatible ways for a physical system to change. It can evolve smoothly, continuously, and deterministically when we are not looking, or it can jump suddenly, discontinuously, and randomly when we perform a measurement. For decades, physicists struggled to accept the reality of this measurement-induced collapse. Albert Einstein was the most prominent skeptic, arguing that the apparent randomness of quantum mechanics must be a mask for some deeper deterministic reality. In 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published the famous EPR paper, designed to show that quantum mechanics was incomplete. They proposed a thought experiment involving two particles that had interacted and then flown apart in opposite directions, becoming what we now call entangled. According to quantum mechanics, if you measure the property of one of these entangled particles, say its spin along a particular axis, its wave function collapses, instantly determining the spin of its distant partner, no matter how far apart they have traveled. Einstein argued that this spooky action at a distance was physically impossible, as it would require information to travel faster than the speed of light, violating the principle of locality. Therefore, Einstein concluded the particles must have possessed definite values for their spins all along before any measurement took place. Quantum mechanics was simply failing to describe these pre-existing hidden variables. This debate remained in the realm of philosophy until 1964, when John Bell realized that Einstein's assumption of local realism could be tested in a laboratory. Bell showed that if particles truly possess definite properties before measurement, and if no influence could travel faster than light, then there was a strict mathematical limit on how strongly the measurement results of two distant particles could be correlated. He formulated this limit as a mathematical inequality. If quantum mechanics was correct and particles did not possess definite properties before measurement, then certain experimental setups would produce correlations that exceeded this classical limit, violating Bell's inequality. The first serious experimental tests of Bell's inequality were performed in the 1970s, but they were plagued by loopholes, potential classical explanations for the observed correlations. For example, the detection loophole arose because the experimental detectors were inefficient, registering only a fraction of the entangled particles. A skeptic could argue that the detected particles were not a representative sample, and that the unobserved particles would have satisfied Bell's inequality. The locality loophole arose because the settings of the measurement devices were chosen in advance, meaning that a subluminal signal could theoretically have traveled between the detectors, coordinating their behaviors. To close these loopholes, physicists embarked on a decades-long campaign of experimental refinement. In 1982, Alain Aspect and his team in Orsay, France, performed a landmark experiment that closed the locality loophole. They used a sophisticated system of rapid optical switches to change the settings of the detectors while the entangled photons were already in flight. The choice of which spin axis to measure was made so quickly that no signal traveling at the speed of light could have crossed the distance between the detectors in time to coordinate the results. Despite this, the photons violated Bell's inequality, behaving in perfect accordance with the non-local predictions of quantum mechanics. Over the next 30 years, experimentalists continued to close the remaining loopholes. Anton Zeilinger and his group in Vienna pushed the boundaries of Bell tests even further, performing experiments across the Canary Islands over distances of more than 100 kilometers. They even used light from distant astronomical quasars, billions of light years away, to determine the measurement settings, ensuring that any potential coordination between the detectors would have had to occur in the deep primordial past, long before the Earth or the Sun had even formed. Finally, in 2015, multiple research groups around the world announced loophole-free Bell tests, simultaneously closing both the detection and locality loopholes in a single experiment. The verdict was absolute. Local realism is dead. The universe does not possess definite hidden properties that are simply waiting to be measured. The death of local realism forced physicists to confront the question of how the macroscopic world of our everyday experience emerges from this fluid subatomic landscape of probabilities. If realism fails at the quantum level, how does it succeed so brilliantly at our scale? The key to this transition is the process of decoherence, which explains how a quantum system's delicate state of superposition is destroyed through its interactions with the surrounding environment. To understand decoherence, we must look at how quantum systems exchange information with their surroundings. When a quantum system is perfectly isolated, its wave function can maintain its coherence, meaning that the different components of its superposition can interfere with one another, producing non-classical effects. But in the real world, perfect isolation is almost impossible to achieve. Even in the deepest vacuum of space, a particle is constantly interacting with stray photons, cosmic background radiation, and dust. When an electron exists in a superposition of being in two different places, its electric field interacts with the surrounding environment. Every photon that bounces off the electron carries away a tiny shred of information about its position. As more and more photons interact with the electron, the information about its superposition becomes distributed or entangled across an astronomical number of environmental degrees of freedom. The phase relationships that allow the different parts of the electron's wave function to interfere with one another are not lost. They are simply dispersed into the environment, becoming completely unreadable to any local observer. This process occurs with astonishing speed. For a macroscopic object like a grain of dust or a human being, the time scale of decoherence is unimaginably tiny. This is why we never see macroscopic objects existing in superpositions. It is not because the laws of quantum mechanics stop working at our scale. It is because the environment is constantly, relentlessly performing measurements on everything around us, forcing the quantum coherence to bleed away almost instantaneously. Decoherence effectively launders the quantum probabilities, turning a coherent, non-classical superposition into a simple, classical mixture of probabilities, where objects appear to have definite pre-existing positions and properties. But while decoherence explains why we do not see quantum weirdness in our daily lives, it does not solve the fundamental mystery of the wave function collapse. It explains how a quantum superposition becomes indistinguishable from a classical probability distribution, but it does not explain how a single, concrete outcome is selected from that distribution. To address this deeper mystery, physicists have had to look beyond the standard Copenhagen interpretation, exploring radical new frameworks that challenge our most basic assumptions about the nature of existence. One of the most active areas of modern research is the study of macroscopic quantum systems, systems that are large enough to see and engineer, yet remain fully quantum in their behavior. For most of the 20th century, quantum mechanics was treated as a theory of the very small, while classical physics ruled the macroscopic domain. But the development of superconducting electrical circuits has completely obliterated this scale barrier. The key to these macroscopic quantum devices is the physics of superconductivity. When certain metals, such as niobium or aluminum, are cooled to temperatures within a few millikelvins of absolute zero, their electrical resistance drops to exactly zero. At these extreme temperatures, the thermal vibrations of the metal's atomic lattice are frozen out, allowing electrons to pair up into Cooper pairs. These Cooper pairs move through the metal as a single coherent quantum fluid, described by a single macroscopic wave function with a unified quantum phase. By inserting a thin insulating barrier between two superconductors, physicists can create a Josephson junction, a device that behaves as a nonlinear, lossless inductor. When an electrical current is driven through a Josephson junction, the Cooper pairs can tunnel through the barrier without any resistance. The phase of the macroscopic wave function on one side of the barrier becomes coupled to the phase on the other side, creating a highly nonlinear relationship between the current and the voltage across the junction. This nonlinearity is what makes superconducting qubits possible. A standard linear inductor combined with a capacitor creates a harmonic oscillator, a circuit whose energy levels are spaced at equal intervals. Because the energy levels are equally spaced, a microwave pulse of the correct frequency will drive the circuit through a continuous ladder of states, making it impossible to isolate a single pair of levels to act as a qubit. But the nonlinearity of the Josephson junction breaks this equal spacing, creating an anharmonic oscillator. The energy difference between the ground state 0 and the first excited state 1 is unique, allowing physicists to use precise microwave pulses to drive the circuit between these two states, or to prepare it in a superposition of both, without exciting any higher energy states. These superconducting qubits are truly macroscopic. They are fabricated using standard photolithography techniques on silicon chips with dimensions that can be measured in micrometers or even millimeters. They contain billions of individual electrons and Cooper pairs, yet they can be prepared in quantum superpositions, entangled with other qubits across a chip, and measured with high fidelity. The development of these devices has turned quantum mechanics from a descriptive science into an engineering discipline, enabling the creation of the first NESQ, noisy intermediate scale quantum, computers. But the engineering of these macroscopic quantum systems is not just about computing power. It is also about testing the foundations of physics. By building larger and more complex quantum circuits, physicists are directly exploring the boundaries of decoherence, testing whether there is any fundamental limit to the size of an object that can exist in a quantum state. Already, researchers have succeeded in preparing mechanical resonators, tiny, vibrating silicon beams containing trillions of atoms in quantum superpositions, demonstrating that even mechanical motion can obey the laws of quantum mechanics if the system is sufficiently isolated from its environment. This experimental program has profound implications for our understanding of the relationship between quantum mechanics and general relativity. If macroscopic objects can exist in quantum superpositions, then what happens to the gravitational field they generate? According to general relativity, any mass curves the surrounding spacetime, creating gravity. If a heavy object is prepared in a superposition of being in two different places, does the gravitational field it generates also exist in a superposition? Does spacetime itself become entangled with the quantum state of the object? To answer these questions, physicists are actively developing experiments to measure the gravitational coupling between quantum systems. One proposed setup involves preparing two massive microscopic beads in quantum superpositions of different paths, and then bringing them close enough to interact solely through their mutual gravitational attraction. If the gravitational interaction can entangle the two beads, it would prove that gravity is a quantum force, and that spacetime must possess a quantum structure at the smallest scales. This search for a quantum theory of gravity has led to a profound convergence between quantum mechanics, general relativity, and the physics of information. One of the most striking insights of this convergence is the realization that information is not just a description of physical systems, but is itself a fundamental physical quantity that obeys thermodynamic laws. This connection was first explored in detail by the physicist Leo Szilard in 1929 in his analysis of the classic Maxwell's demon thought experiment. In 1867, James Clerk Maxwell proposed a thought experiment to challenge the second law of thermodynamics, which states that the entropy or disorder of an isolated system must always increase over time. Maxwell imagined a container divided into two chambers by a partition with a small door. A tiny, intelligent being, the demon, guards the door, measuring the speeds of the gas molecules as they approach. When a fast, hot molecule approaches from the left chamber, the demon opens the door, letting it pass into the right chamber. When a slow, cold molecule approaches from the right, the demon lets it pass into the left. Over time, the demon sorts the molecules, heating the right chamber and cooling the left, without doing any work. This sorting action decreases the entropy of the system, apparently violating the second law of thermodynamics. For nearly a century, physicists struggled to find the flaw in Maxwell's thought experiment. The demon seemed to be able to violate the second law simply by being clever, using its intelligence to bypass the thermodynamic constraints of matter and energy. The resolution to the paradox was finally found when physicists began to treat information as a physical quantity. In 1929, Leo Szilard showed that the demon must perform a physical measurement to determine the speed of the molecules, and that this measurement must carry a thermodynamic cost. But the final definitive resolution was provided by Rolf Landauer in 1961 and Charles Bennett in 1982. They realized that the demon's mind, or its physical memory register, is a physical system that must obey the laws of thermodynamics. As the demon sorts the molecules, it must store the results of its measurements in its memory. Because any physical memory has a finite capacity, the demon will eventually run out of space and must erase its memory to continue sorting. Landauer proved that the erasure of information is a fundamentally irreversible thermodynamic process. When you erase a bit of information, resetting it from an unknown state to a known state, you are reducing the entropy of the memory register. To satisfy the second law of thermodynamics, this local reduction in entropy must be accompanied by the dissipation of heat into the surrounding environment. This minimum energy cost, known as the Landauer limit, equals the temperature of the system multiplied by Boltzmann's constant and the natural logarithm of 2. Landauer's principle establishes a direct quantitative link between information theory and thermodynamics. It shows that information is not an abstract, disembodied concept. It is physical, and its manipulation has inescapable thermodynamic consequences. You cannot delete a file from a hard drive or reset a qubit in a quantum computer without dumping a microscopic amount of heat into the universe. Information is as real and physical as mass, charge, or energy. This deep connection between information and physics has taken center stage in modern research into the nature of black holes. Black holes are the most extreme environments in the universe, regions of space-time where the gravitational pull is so intense that nothing, not even light, can escape once it crosses the event horizon. According to classical general relativity, black holes are incredibly simple objects, described completely by just three properties: their mass, their electric charge, and their angular momentum. All other details about the matter that collapse to form the black hole are completely lost behind the event horizon, a property known as the no-hair theorem. But in 1972, the physicist Jacob Bekenstein realized that this simplicity created a thermodynamic crisis. If you throw a hot cup of tea into a black hole, the entropy of the tea appears to vanish from the universe, violating the second law of thermodynamics. Bekenstein proposed that to save the second law, black holes must possess their own intrinsic entropy, and that this entropy must be proportional to the surface area of the event horizon rather than its volume. Bekenstein's proposal was confirmed in 1974 by Stephen Hawking, who combined quantum field theory with general relativity to show that black holes are not completely black. Hawking discovered that quantum vacuum fluctuations near the event horizon cause black holes to emit a steady stream of thermal radiation, now known as Hawking radiation. This radiation carries away mass, causing the black hole to slowly shrink and eventually evaporate completely. By calculating the temperature of this radiation, Hawking was able to determine the exact constant of proportionality for Bekenstein's black hole entropy. The result is the famous Bekenstein-Hawking entropy formula, which states that the entropy of a black hole is equal to its surface area divided by 4 times the Planck area, the square of the Planck length. This formula is one of the most beautiful and mysterious equations in all of physics, as it directly connects gravity, the Planck length, thermodynamics, entropy, quantum mechanics, Planck's constant, and relativity, the speed of light. But the formula also introduced a profound mystery, known as the holographic principle. In standard statistical mechanics, the entropy of a physical system is proportional to its volume, as the number of degrees of freedom increases with the amount of space available. But a black hole's entropy is proportional to its area. This suggests that the maximum amount of information that can be stuffed into any region of space is determined not by its three-dimensional volume, but by its two-dimensional boundary. It is as if our three-dimensional world is a holographic projection with all the fundamental information encoded on a distant two-dimensional screen. This holographic view of the universe was given a precise mathematical formulation in 1997 by Juan Maldacena, who discovered the ADS-CFT correspondence. Maldacena showed that a specific theory of gravity operating inside a five-dimensional spacetime, known as anti-de Sitter space, is mathematically completely equivalent to a flat, four-dimensional quantum field theory, a conformal field theory, operating on the boundary of that space. The ADS-CFT correspondence is a true duality. Any calculation that is incredibly difficult to perform in the gravitational bulk can be translated into a much simpler calculation on the quantum boundary, and vice versa. It shows that gravity, and indeed space-time itself, can be viewed as an emergent phenomenon arising from the complex quantum interactions of particles living on a lower dimensional boundary. This holographic framework has recently provided the key to resolving the black hole information paradox. In 2019 and 2020, physicists utilized the ADS-CFT correspondence to calculate the entropy of the Hawking radiation emitted by an evaporating black hole. They discovered that the calculation of the gravitational path integral must include contributions from quantum extremal islands, regions deep inside the black hole interior that, through the magic of extreme quantum entanglement, mathematically belong to the radiation system outside at late times. By including these quantum extremal islands in the calculation, physicists showed that the entropy of the Hawking radiation follows the Page curve, rising as the black hole evaporates and then declining to zero as the black hole vanishes. This proved that the information about the matter that fell into the black hole is not lost. It is preserved in the subtle non-local quantum correlations between the emitted photons of Hawking radiation, satisfying the quantum principle of unitarity. The information is not destroyed, it is simply scrambled across the cosmic ledger. This modern resolution of the information paradox highlights the absolute centrality of quantum entanglement in the structure of spacetime. It is not just that spacetime contains entangled particles. Rather, spacetime itself is constructed out of entanglement. This is the core insight of the Ryu-Takayanagi formula, formulated in 2006, which relates the entanglement entropy of a subregion on the holographic boundary to the area of a minimal surface extending into the gravitational bulk. The Ryu-Takayanagi formula is the smoking gun of emergent geometry. It shows that the distance between 2 points in the bulk spacetime is directly proportional to the amount of quantum entanglement between the corresponding degrees of freedom on the boundary. If you decrease the entanglement between two boundary regions, the minimal surface connecting them in the bulk stretches and grows. If you reduce the entanglement to zero, the spacetime fabric literally tears itself apart, disconnecting the two regions entirely. Spacetime is not a smooth, continuous stage upon which the drama of physics plays out. It is a macroscopic web woven from the invisible threads of quantum entanglement. This realization has led to a profound shift in how we think about the fundamental laws of nature. In the classical reductionist view, the goal of physics was to find the smallest, most fundamental building blocks of matter, the quarks, leptons, and gauge bosons, and the forces that govern their interactions. But in a holographic, emergent universe where space-time is synthesized from entanglement, this reductionist approach must be replaced by a holistic, information-centric perspective. In this view, the fundamental quantity of the universe is not matter or energy, but quantum information. The properties of particles, their mass, charge, and spin, are not intrinsic qualities of solid corpuscles. They are the emergent signatures of how quantum information is processed, conserved, and routed through the cosmic network. The laws of physics are the rules of this information processing system, the cosmic software that dictates how quantum states can be transformed and entangled. This perspective has given rise to several radical new interpretations of quantum mechanics that seek to place information at the very heart of the theory. One of the most prominent is cubism, or quantum Bayesianism, developed by Christopher Fuchs, Rudiger Schack, and others in the early 2000s. Cubism combines quantum information theory with the subjective Bayesian interpretation of probability. According to cubism, the wave function is not an objective physical entity waving in an abstract Hilbert space. It is a subjective mathematical tool used by an individual agent to represent their personal beliefs about the outcomes of future measurements. When an agent performs a measurement, the collapse of the wave function is not a physical event occurring in the external world. It is simply the agent updating their beliefs in response to new data in perfect accordance with Bayesian probability theory. Cubism completely eliminates the measurement problem by declaring that the quantum state is entirely subjective. There is no objective wave function of the universe that needs to collapse, and there is no paradox of Schrödinger's cat being both alive and dead. The cat superposition is not a physical state of the cat. It is a representation of the observer's uncertainty. Once the observer opens the box, they gather new information and update their personal state assignment, resolving the uncertainty. Another closely related approach is relational quantum mechanics, RQM, proposed by the Italian physicist Carlo Rovelli in 1996. RQM takes its inspiration from Einstein's theory of relativity, which showed that properties like velocity, time, and space are not absolute, but exist only relative to a specific frame of reference. Rovelli argued that quantum mechanics requires a similar relational revolution. According to RQM, there are no absolute observer-independent values for physical properties. An electron does not possess a definite position or spin in itself. It only possesses a position or a spin relative to another physical system with which it has interacted. A measurement is simply any physical interaction between two systems, and the outcome of that measurement is a relational fact that exists only for those two systems. This relational perspective is beautifully illustrated by the Wigner's friend paradox. In this thought experiment, a physicist, Wigner's friend, is inside a closed laboratory performing a measurement on a quantum system in a superposition. According to the friend, The measurement has occurred, the wave function has collapsed, and they have observed a single definite outcome. But to Wigner, who is standing outside the closed laboratory, the entire lab, including the friend and the measurement device, is a single, massive quantum system that has evolved into an entangled superposition of all possible outcomes. In the standard Copenhagen interpretation, this is a deep paradox. Has the wave function collapsed or not? But in relational quantum mechanics, the paradox dissolves. The measurement outcome is a relational fact that exists relative to the friend but does not yet exist relative to Wigner. Wigner will only resolve the superposition and observe a definite outcome once he opens the lab door and interacts with the friend, establishing a relational link between them. There is no single, objective view from nowhere that can describe the absolute state of the universe. This relational view of reality has been sharpened in recent years by new mathematical theorems, such as the Frauchiger-Renner theorem, published in 2018. This theorem uses a sophisticated, multi-observer extension of the Wigner's friend thought experiment to prove that quantum mechanics cannot satisfy three basic intuitive assumptions simultaneously: that the theory is universally applicable to observers of all scales, that different observers can arrive at consistent, mutually compatible descriptions of reality, and that a measurement yields a single, definite outcome for all observers. The Frauchiger-Renner theorem shows that if we want to preserve the universal validity of quantum mechanics, we must abandon the idea of a single, objective, observer-independent reality. Different observers, looking at the exact same physical events from different perspectives, can arrive at completely contradictory, yet internally consistent and mathematically valid descriptions of what occurred. Reality, probed deeply enough, is fundamentally perspective-dependent. This perspective-dependent nature of reality is not a failure of our scientific instruments or our cognitive faculties. It is a fundamental property of the mathematical structure of the universe. It is the inescapable consequence of living in a universe described by a complex valued wave function that evolves in Hilbert space and collapses through the generation of relational entanglement. As we stand on the frontier of this research, we are beginning to see how these abstract, philosophical insights can be harnessed to create entirely new classes of technology. The development of quantum communication networks, quantum key distribution, and quantum computers is not just about building faster, more secure devices. It is about learning to navigate and manipulate this perspective-dependent, information-centric reality with engineering precision. By learning to control the delicate phase relationships that govern quantum superpositions, we are developing the ability to perform calculations that would be impossible on any classical machine. We are learning to exploit the non-local correlations of entanglement to transmit information with absolute security, protected by the laws of physics themselves. We are beginning to build materials whose properties are designed from the ground up by manipulating their quantum phase structures, creating superconductors that operate at higher temperatures and topological materials that are immune to decoherence. And yet, as our technological power grows, the mystery at the heart of the theory only deepens. We are building machines that exploit the collapse of the wave function every single day, yet we still do not know what the collapse actually is or why it occurs. We are engineering devices that leverage the emergent geometry of space-time, yet we still do not have a complete, mathematically consistent theory of quantum gravity. We are using information to rewrite the laws of thermodynamics, yet we still do not know if information is the fundamental substrate of existence or simply a human metaphor that we project onto the dark, unyielding canvas of the cosmos. Perhaps the ultimate lesson of quantum mechanics is that the search for a single, final, objective theory of everything is a classical dream that we must let go. In a participatory, relational universe where the act of measurement brings properties into existence and where different observers can experience different valid realities, there may be no single objective truth waiting to be found at the end of the scientific rainbow. Instead, we may have to accept a richer, more open, and more beautiful picture of the cosmos. A cosmos that is not a static collection of facts, but an ongoing, dynamic, and self-creating dialogue between information, geometry, and observation. It is a universe that does not exist independently of our questions, but is brought into focus, step by step, through the very act of our looking. We are not passive spectators watching a pre-written play. We are the co-authors, the participators, and the instruments through which the universe continuously writes its own magnificent and deeply strange future. Let us continue to write.